Alright, we are back. So, on Tuesday, we spent the time talking about uncertainty that's associated with the graph, right? Each individual point on this graph, we can represent its uncertainty with a set of error bars, right? Depending on how much uncertainty there is in each of those individual measurements. We talked about, or they discussed in the review packet, that in theory, we could have different error bars for each individual measurement, although the way I see it, if you're using the same measuring tool each time, your uncertainty in each measurement should be the same because your uncertainty comes from that measurement. So anyway, they said if you have a situation like this where you have error bars of different sizes for different measurements, you don't necessarily have to represent them that way on the graph. That a lot of times, if you just take the biggest range for any of your measurements and use that as the range for all of your measurements, that's going to encompass all of the uncertainty and will be involved with that. Right? So that's how we represent uncertainty on a graph. Then using that graph to get some information like the slope or the intercept, basically you're going to take the steepest possible slope. So take the highest level of the uncertainty here, the lowest level of the uncertainty here, draw a line. That's the theoretically steepest possible slope we could have. And then for the other one, you're going to start at the lowest level of uncertainty here, the highest of the range of uncertainty here. That's your, in theory, shallowest possible slope. And then as far as the intercept goes, just wherever those two lines meet, that would be the uncertainty range of your intercept. Okay? So then we started talking about this sample test, and Haley, I gave that to them on Tuesday. So we went through the uncertainty involved with this graph and the different measurements of this graph, and we drew the different lines of the slope. Right? Oh, did I not put those? I really thought I had them in here. Anyway, wherever they ended up. So we're gonna start on page 4 of that test, which is question number 2. It says, student used an electric timer in an attempt to estimate the acceleration of free fall g. She measures the time t taken for a small metal ball to fall through a height h of 0.5 meters. The percentage uncertainty in the measurement of time is 0.3%. Percentage uncertainty of height is 0.6%. So it says, using this formula, h is equal to 1/2 g times t squared, which is just one of our equations for uniform motion that we'll discuss maybe by the end of the day today. Maybe not, though. We'll see how far we get. So it says, calculate the expected percentage uncertainty in the value of g. Okay? So, nope. Where did I put it? There it is. Okay. So it says, calculate the expected percentage uncertainty in the value of g. First thing we're going to do here is rearrange this equation to get g by itself. So now, in order to get g, we're actually going to have to do 2 different mathematical operations. The first one we're going to have to do is a division problem. Actually, that's not the first one we're going to have to do. The first one we're going to have to do is this exponent in the time. And then the second one is a division problem dividing h by t squared. Okay? So mathematical operations, we handle them differently as far as the type, how we handle this, or how we handle the uncertainty. So going back to this page right here. Okay? When we do powers here, okay, the important part basically is whenever we're taking something to a power, we're going to multiply its uncertainty by the number of times we're taking it to that power. Okay? So in this case here, we know that the uncertainty in time is 0.3%, and we're taking time to the second power. So that uncertainty there, we're just going to multiply that like this. So the uncertainty in this entire mathematical operation is 0.6%. Okay? Does that make sense? Okay. So whenever we're taking something to the power, we're just multiplying it, multiplying the uncertainty in that value by however many times we're raising it to that power. We've handled the uncertainty now in the bottom of that fraction, so now we go back over here, and like we discussed, and we did a problem like this the other day, when we are multiplying the addition of the percentage uncertainties. So in this case here, if we're trying to calculate the, in this example, we were trying to calculate the density because it was mass over volume. The percent uncertainty in the mass was 10, the percent uncertainty in the volume was 4. Sorry, we're calculating density, mass over volume, right? So we did there, the total uncertainty is just the addition of those two. Alright? Going back and applying that to this one, we're dividing h by t. There is no uncertainty in the 2, so we don't have to worry about that. That's just a value, right? So the uncertainty in h is 0.6. The uncertainty is t is also 0.6 because we had to multiply it by that 2 to begin with. So the overall uncertainty in g is going to be the uncertainty in h plus 2 times the uncertainty in t. Because we're dividing h and t, but we had to take t to that power. Is that okay with that? Okay. And so this we got was 0.6. We already calculated that the total uncertainty in t after raising it to the power is 0.6, and so the overall uncertainty in our value of g would be 1.2%. That good, Fuad? You got it? Does it make sense? Okay. So with the mathematical power, we're just multiplying the uncertainty in the individual measurements by the number of times we're raising it to that power. Okay? So we're squaring t. Individually, t has an uncertainty of 0.3, so we just multiply 2 times 0.3 to get 0.6. Okay? Then, to get g, we're dividing h by t. Okay? We're dividing h by t squared, actually, right? Whenever we divide two things, we just add the uncertainties of those individual measurements to get the total uncertainty. So the total uncertainty in g is the uncertainty in h plus the uncertainty in t, but because we raised it, we have to take that uncertainty of t and multiply it by 2. Does that make sense? And that's where the 1.2 comes from. Yeah, because in this, like, Haley, that comes from here, right? That's not a measurement, that's an exact value, right? That's part of the equation, so we don't have to worry about the uncertainty in that. Same thing, like, if we're doing kinetic energy, and kinetic energy, the formula for kinetic energy, right, is 1/2 mv squared. We don't have to worry about the uncertainty in 1/2 because it's a constant value. It's exactly 1/2. It wasn't a measurement that we took, so we don't have to worry about that uncertainty. Does that make sense? Okay. All right. Overall, how could we get a more reliable value for g? Right. So Haley, this is similar to what you did for your internal assessment, right? They're only dropping it from a height of 0.5 meters, right? And trying to time how long it took to get from the ground, or from the height to the ground, right? It's not enough time, right? So what can we do to decrease that percentage? Increase the height. That's one way we can do it. Okay. The other way we could do it would be, there's another way we could do it too. What are we assuming about this fall? Yes. What else are we assuming it has something to do with gravity? Sure. Yeah, that's super technical. But what is this measuring? The acceleration of what? Don't overcomplicate it. The acceleration of what? Gravity. Is gravity the only thing affecting that object? What else? Air resistance, right? We can't necessarily get rid of air resistance, but we can do something to what we could, if we have access to a vacuum, sure, right? So, it's not on my schedule, but so.
Okay, well, I'm sorry for interrupting.
That's okay. So, hold on, wait. So, if we can get rid of the air, that would obviously be the best choice, right? But there's some things we can do to reduce the amount of air resistance, right? So what can we do to reduce the amount of air resistance? Decrease surface area, right? What else could we do? Decrease surface area. What other kind of ball is about that same size, Fuad? It's also white. Right? A ping pong ball is about that size, right? But it's less dense. So if we increase the density, reducing the surface area, increasing the mass, right, that's going to give you better results because you don't have, because air is not accounted for in this, air is not accounted for here. So if we can reduce the amount of air resistance as much as possible, then, right. Yep. The other thing that we talked about was what? Increase height, right? Because then you're not having as much uncertainty about starting and stopping times. Well, the uncertainty in your starting and stopping times is about the same, but there's a much longer fall time in between. Yeah. More trials is another way. Yeah, more trials is another way. So if you look here, I'll show you all the things that they listed that are possible. Those are all the things that they listed. So, yeah, you guys did a good job, right? Smaller ball, reduce air resistance, height, repeat it more times. You can also go with the graph because the graph then builds in the uncertainty into the graph, and then you could reduce that uncertainty that way. You're supposed to have 3 of those, yes. So. I bet you, and I'm not totally sure on this, but if you said reduce it, you do it in a vacuum, like, that could be one too. All right. Oh, too far. Okay. Fuad, here you go, Fuad. It's time to lend us your expertise. So. Likes meat. If this question was about meat, Fuad would be all over it. What, are we having meat tomorrow evening? Are we having beef, chicken, and shrimp, or no? Cooked in a calorimeter. All right, so it says, an experiment to measure the specific heat capacity of a metal, a piece of metal is placed inside a container of boiling water at 100 degrees Celsius. The metal is then transferred into a calorimeter of water containing water at a temperature of 10 degrees Celsius. The final equilibrium temperature of the water was measured. One source of error in this experiment is that a small mass of boiling water will be transferred to the calorimeter along with the metal. All right? So it says, suggest the effect of the error on the measured value for the specific heat of the metal. So, Fuad, in order to get the specific heat of the metal, you actually have to do 2 calculations, right? What do you have to do first? Not the specific heat of the water. What do you have to? No. What do you have to do first? What's the first calculation that you did, Fuad? Oh, I should do this. Hold on. For what? The energy of what? That's the first calculation that you have to do for the water. Okay? That's the first calculation that you do. Yep. That's right. So now, here, the error that they're telling us about, right, is that a small mass of boiling water will be transferred to the calorimeter along with the metal. When you did this experiment, the mass of water that you measured, you did it before you put your substance into the water, right? So now, what actually is happening to this mass value? It's not going way up. Like, it's going up a little bit because it's like all we're talking about here is the water that is the water that is stuck to the piece of metal when you put it in. Yeah. So we're not talking about a lot. No, no, no. This, you have to do this calculation for the water first, right? And then with this, you rearrange that equation for the metal, but this, it goes there because of the whole conservation idea. So if you know how much heat energy the water in the calorimeter gains, you'll know how much heat energy the metal loses. Does that make sense? Because of conservation, right? If one's gaining energy, the other one has to be losing energy, right? Yeah. So in this case, Fuad, right? You measured the mass of the water, but it's actually lower than the mass of water that's in the calorimeter now because we've brought some water with it, right? So the Q, the heat, is based on the water that was already in the calorimeter plus the water you brought into it, but your mass is only based on the mass of water that was in the calorimeter to begin with. Does that make sense? So, say again. It won't make a huge difference, most likely, but it is a source of error, right? So, yeah. So in this case here, the mass that you're using in this calculation is too small. Does that make sense? Right? So if one factor in this equation is too small, it's going to make this too small. Is that right? Because, you know, both sides of the equation. So in this case here, incorrect M for water means Q for water too small. And then, if we use a too small Q value over here and bring it over here, that's too small. What? Right. And if the top of this fraction is too small, what is that going to do to this C value? It's going to be too small as well, right? Is that, you follow me on that? Right? And that's just more of a following the math kind of thing, right? You know, if this is too small, that's going to be too small. If that's too small, this is too small, blah, 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 blah. Good? Okay. Flood, what are some other sources of error in this experiment? Water evaporating. Non-insulated system. Right. Yeah, when we move it from when we move the metal from the hot water bath to the calorimeter, we're losing some of that heat there, right? If we spill some of the water, like when we drop the metal in and spill some of the water out of the calorimeter, that can be a source of error too, right? Say again? Yeah, that's not one. Yeah, 'cause that's not error. That's uncertainty, right? That we incorporate that into our measurements, but we don't incorporate for the fact that we lose energy transferring that metal from the hot water to the cold water into our measurements or into our calculations. You know what I'm saying? There's a difference between reading the thermometer and something that you really can't control. You know what I'm saying? Or at least is much harder to control, right? So they have here, right? Metal may not have been heated uniformly, okay. Metal may not all be at 100 degrees Celsius, so, right, we took care of that with putting those things, putting your substances in the like in the freezer overnight or in the refrigerator overnight to try and make sure that all of that was the same temperature. Energy lost to air during the transfer. Energy may be lost through air through the calorimeter. Water may not be at uniform temperature. So yeah, these are all things that aren't reading the thermometer wrong, but they're things wrong with the procedure that may lead to some uncertainty in our answer. Okay. Yeah, I'm not sure, because the bald answer usually is no unit. And like when there are calculations, it says don't allow a bald answer. That bald answer is a unit, but I'm like, there's no unit here. I don't know what the deal is with that. So, all right, good there. Okay. All right, let's go here. This is the pages that I sent to you guys in the mail the other day, or through email the other day. But I printed them out for you so we can talk about this stuff. All right. So this is straight from the review book for our physics book. So you can see that it's, you know, the cover looks pretty similar, right? So we start off talking about motion, and there's basically three things that we want to know about a motion, right? About a motion, not emotion, right? Okay. Displacement, velocity, and acceleration. Okay. Displacement is how far away we are from the starting spot. The distance moved in a particular direction. Okay. Velocity, the rate of change of displacement. So how quickly is that velocity changing? Whenever we talk about rate, it's always a time, right? So like it says, change in displacement over the time taken for it. Speed is the rate of change of distance. Important thing for us to remember, speed and velocity are not the same thing, right? Speed's a scalar, velocity is a vector, right? Basically, they're different as long as we don't do what? As long as the direction doesn't change. As long as we're going in a straight line, speed and velocity are the same thing. But as soon as we change directions, either in one dimension, turning around and coming back the other direction, or in two dimensions, turning the corner, then speed and velocity become different. Okay? And then finally, acceleration, the rate of change of velocity. So again, because it's a rate, we have a change in velocity over time. Okay? Up at the top, things to keep in mind, and this goes back to like one of the things that we talk about at the very beginning of physics. If we don't keep our vocab straight, we can run into some issues, right? Speed and velocity aren't the same thing. Acceleration doesn't necessarily mean speeding up, right? Those kind of things that they're warning you about those up there. Okay? All right, at the bottom of the first page, instantaneous versus average. Okay? Average is over a large period of time. Instantaneous is at some particular moment in time, right? In the first 2 seconds of this race, this runner girl goes 10.04 meters. we can figure out her average velocity by taking 10.04 and dividing it by 2. But that's not how fast she's going at that very moment. That was her average. She's going faster than that here because she had that, her average is 5, so half the time she had to be going less than that, and the other half of the time she had to be going more than that. Does that make sense? Right? So there is a difference between instantaneous and average. Average is over a span of time. Instantaneous is at a particular moment. Say again? Exactly. Which is when we get into like our kinematic equations, then we can say, okay, that's the instantaneous velocity when we talk about like the kinematic equations are functions. We use a bunch of different letters in it, but they're functions of time basically. And it's just a matter of which factors do we have. And like we said, in order to solve them, you need to know 3 of the items in there because you're basically solving an equation, a function that has multiple terms in it. But if you're going to solve it for one specific term, you got to know the other 3 terms, you know what I'm saying? This here, we know the distance or the displacement that she goes. We know that it takes 2 seconds to get there. We know her initial velocity is 0. So we could figure out what her final velocity is. But one assumption that we make about our kinematic equations is that acceleration is constant. And that's not always the case when we have a girl running a race. Say again. Just more that she can't maintain. Like, there's a huge acceleration at the beginning of the race. Like I said, to win a race, you want to go as fast as possible, as quickly as possible, and then maintain that top speed as long as you can, you know, because that's going to increase your average velocity. So we could use a function here if we assume that the acceleration is constant. But yeah, those kinematic equations, they're just functions that. Mm-hmm. It's really not.
Like F equals MA letters?
Yeah, I mean it's just.
Well, I mean it's not that
the concept is there, but when you think about what the differentials mean and what the integrals mean, it's like, oh, like that's why we do it. So you know, it's not as, if you understand the concepts, then the math is like, oh, that's just why we do that. You know. So. All right, so that's instantaneous versus average. All right, frames of reference. Right? We have to decide where we're looking at things from, and that may change how we describe something, but it's not changing what happens, right? If we're on a highway, right, the car on the top is going 30 meters per second, the car on the bottom is going 25 meters per second. If you ask the guy in the car, this car on the top, what this car is doing, he would say it's moving backwards. Does that make sense? If you ask this guy in this car, what this car is doing, it's moving forward. That doesn't change what they're actually doing. They're still both moving 30 meters per second, 25 meters per second, but how we describe them is actually a little different. Yeah, your frame of reference determines how we describe those things. It really doesn't matter. Any answer is just as valid as any other answer. It's just a matter of how we describe it. Good. Yeah.
If somebody's in a train,
Yeah.
and there's a zebra outside,
Yeah.
and lightning strikes at the beginning of the train, do they both see it at the same time?
Yes. Because the lightning is not a part of the train. If there was, let's say, like a guy in the train went and shocked somebody else on the train, well, if he was going to speed of light, you wouldn't be able to see it, right? But if he went up and shocked somebody on the train, it would look exactly the same as if you shocked somebody in your house. But to the person off the train, they would see like a real slow finger, and then they could like see the lightning come out of the finger and shock the person, because you only observe that time dilation from outside of the moving frame of reference. Right? Does that make sense? It is totally weird. So, but with that lightning, it's not in either one of their frames of reference, so they should see it the same. Does that make sense? All right. So here, next, we can help establish patterns in analyzing motion by looking at graphs. Right? We talked about in the last part that we make graphs to look for patterns. Okay. And you said this gets a little bit more into the math stuff. Okay. When we take a graph, there's basically two things we can look at on that graph. The first one is the gradient of the graph, or the slope of the graph, which in calculus is what? It's the derivative, right? Like that's what the slope of the line is, or the slope of the curve is the derivative, right? The second thing we can do is we can find the area under the graph, and that's your integral, right? So when you think about what derivatives and integrals do, it helps to understand the relationship between those motions. Yeah, it is. And I mean, when you guys get into calculus, you do a bunch of physics problems, don't you? Like that's kind of how we use it, because those relationships are really holding true there. So yeah. So, but when we first start with these graphical representations of motion, we basically start with a bunch of straight graphs, because it's much easier to find slopes and areas underneath the graph on straight graphs than it is on curved graphs, right? So, displacement time graphs. Graphs that show, right? Graphs that show where you are at a certain time, okay? The slope on a displacement time graph tells you the velocity. Okay? Meaning, straight lines on a displacement time graph are constant velocities, because the slope is constant. Doesn't tell you anything. It's like, say again? This one? This one gives you displacement. So. Momentum isn't going to be on any one of these graphs, because momentum is mass times velocity, and mass doesn't show up on these graphs anywhere here, right? So the interesting one is velocity. So we'll talk about that one in a second. If you take the area underneath the curve here, you get displacement times time, so meters times seconds, which physically is not any kind of a meaningful quantity, right? You can do it, but it just doesn't tell you anything. Do I need to write this down, or you guys like? Okay. In this graph, a distance time graph that is curved, bottom left-hand corner here, the slope keeps changing. That's where the derivative comes in. If you found the derivative of this curve and plugged in any specific time, it would give you the instantaneous velocity at that point. It gives you the slope of the tangent line to that curve, which is what a derivative does. Top of this curve, right? It's an inflection point. Slope at an inflection point is what? Or the derivative at an inflection point is what? It's the max. What's the derivative at that point? 0. Because at the top of a motion, the velocity has to be 0. The tangent line would be horizontal. Its slope is 0, but physically the velocity is 0 at that moment too. Does that make that good there? Okay. Velocity time graphs. This is where we get interesting. The slope on a velocity graph tells you the acceleration, because it's the rate of change of velocity. It's meters per second per second. So slope on a velocity graph gives you acceleration. But if you take the area of the velocity graph, or the area under the velocity graph, that will actually give you the displacement. it will give you how far something has traveled. Okay? It is cool. This graph down at the bottom of the middle part is the velocity graph of this graph over here on the left.
Well, that makes a lot of sense to me, 'cause, like, if you, because it's going down.
Yep.
Like, if you look backwards.
Right.
So it would
The
be like,
velocity goes from being positive to being negative, right? Because here, this area would be positive and this area would be negative. So when you add them together, you end up with what? 0.
just going backwards, or, yeah.
That's what that is. That's what that's a graph of. That just like that. So, and so when you take the area now here and this graph up on the top, he speeds up, goes at a constant velocity for a while, and then slows back down, but never has changed direction, always moving forward. So you'll get a positive displacement by adding up here 3 shapes, a triangle, a rectangle, and then another triangle, right? That would all be positive because because he never changed direction. He sped up, he went constant, he slowed down, but it was always going in the same direction. So this displacement is going to be positive the whole time, right? So slope on a velocity graph gives you acceleration. Area under velocity graph gives you the displacement, gives you how far something has gone. Okay? Acceleration graph. The slope really doesn't tell you a whole lot. It tells you the rate at which velocity is changing. I don't know. Yeah, it might be like there may be something for that. Like when you talk about a car accelerating, going from 0 to 60, because a car doesn't accelerate at a constant rate. It has more acceleration in certain parts than other parts and stuff like that. And when you shift gears, that changes the acceleration and stuff like that. So the slope of an acceleration graph tells you the rate of change of acceleration. Mathematically, we can do that, but it doesn't really tell us a whole lot. Here, for the area under the graph, it tells you how much the velocity changes, the actual change in velocity. So the bottom 3 graphs here are all for this same motion of throwing the ball up in the air and catching it in your hand. Displacement looks like this. You can see the changing velocity the whole time. Velocity looks like this. You can see that the velocity changes at a very constant rate. But going from positive 10 to negative 10 on the velocity scale is actually a change of 20, right? Because that direction is important when we're talking about the change in that velocity. Does that make sense? And then finally, that brings us into our equations of uniform motion, which is our kinematic equations, right? And here's the kinematic equations, right? There's 5 of them there. These are the symbols that we use to represent those things in those equations, right? Notice that it has a note here, right? Acceleration is going to be constant. The acceleration has to be constant in order for us to use those equations. Okay? Most of those problems that are in that packet that I gave you actually are kinematic equation questions along the way. It's actually 3 pages of problems, and the very, very back page is the answer to all those problems. So you can check and see how you're doing with that. Okay? Here's what I'll do. I'm pretty sure I will have access to the building as we go over break. I will send you some more little review packety things and go over forces and go over momentum and that kind of stuff as we go through break. So you can start working on some things there, and I'll get you some more practice problems and some answers to go along with it. So, okay, good there. Yeah.